This lecture is a background lecture, and what it will be used for is to situate the context in which we'll discuss modeling for the next two lectures. So models for groups and models for space and time. And so here I'm going to give a sort of introduction, but more on the epi proper side. In terms of what we'll be looking at this lecture, I'll be looking at heterogeneity of spread within a location, and then mobility and the spread of infectious diseases. And I'll say a little bit about the waves of COVID-19 because they illustrate a little bit of a combination of spatial and heterogeneous spread. Now, so to begin with, heterogeneity of spread within a single location. And there are a variety of sources of heterogeneity, but here I'll focus on three particular ones: age structure, social structure, and heterogeneity of the pathogens. So age structure to begin with. Well, you don't have to think very hard to realize that many diseases have different burdens in different age groups. So if you think about diseases such as childhood diseases, measles, mumps, etc., for instance, they confer typically lifelong immunity, and therefore they hit very differently groups that have already acquired such an immunity and groups that haven't. Diseases in which immunity is acquired through repeated exposure. So for example, if you think about malaria, malaria typically kills younger children because they have not yet acquired immunity, but those who survive acquire immunity through repeated exposure to malaria. And so, of course, age groups are going to be very different in terms of how much the disease impacts them. Also, you can think of diseases in which the type of contacts are important. And so, for instance, if you're thinking about influenza, well, kids play with kids more and adults stick with adults more. And so the mixing between individuals is not homogeneous. The models we saw up to now were mostly models that assumed some degree of homogeneity in contacts. If you think a bit, if you tease down the details, clearly there is some heterogeneity in terms of who acquires infection from whom, which is this acronym that is quite used in a variety of contexts. Okay, so this is an example of data in the US, which is showing the number of measles cases among travelers returning to the US as a function of the year in which this happened. And okay, this is not very precise, but what you can see is that those aged more than 19, some years are quite represented, but in most cases, most of the so you can see that, for example, kids aged 6 to 23 months, which is a very small portion of the population, do represent a sizable fraction of the cases that are occurring a given year. Likewise, as I was saying, malaria has very different impacts based on the age. And if you look at this data on the deaths from malaria up to 2019, you can see that, okay, things are getting a little better, but they still overwhelmingly deaths are still overwhelmingly happening within people that are under 5 years old. And the least impacted are those 5 to 49. After 49, when you get a bit older, your immune system starts to not deal as well with repeated exposures, and that's why these age groups start to increase a little bit compared to the 5 to 49. But overwhelmingly, kids under 5 are the ones that are most affected by malaria. This is a graph that's illustrating population contact patterns in the US during the COVID-19 epidemic or pandemic. And what you can see here, so let me move myself out of the way, but it's not really important. What you can see here is this who acquires infection from whom, although this is not who acquires infection from whom, it's more who's in contact with whom. And you can see that the diagonal of these matrices are where most of the contacts are taking place. So because you tend to have contacts more with people of around the same age group as yours. Okay. So age groups are an important source of heterogeneity in contacts. Another source of heterogeneity is social structure. So first of all, I'll point out that social structure, age is of course part of social structure, and so age plays a role there as well. But for instance, there are other social contexts in which the structure plays a role. So for instance, in a country like Canada, we have a large immigration, and newcomers are more prone to developing tuberculosis than established populations. An example I was giving in an earlier lecture, if you think about intravenous drug users and as a risk group for infection by HIV, this is a higher risk age group, group than other groups. Okay, so this social structure plays an important role in heterogeneity, even within a single population. This is another graph that I took from a paper, and by the way, so you can see the reference if you use the presentation mode, which I will not show you here, but the presentation mode shows you the source of this graph. What it's showing is within and between classroom transmission patterns of seasonal influenza in primary schools. Okay, this is in Japan. But what it's showing is really that most transmissions happen within a given classroom rather than between classrooms. Okay. Oops. This is arrivals in Canada from different groups of countries. So this is the percentage, it's not showing in the side here, but this is the percentage of arrivals, new immigrants that are arriving from these 4 groups of countries. So group 1 are countries where the incidence of tuberculosis, so this is tuberculosis. So group 1 have incidence of tuberculosis on average less than 15 new cases per 100,000 people per year. So for context, Canada, the average for the country is 3.5, I believe, or 3, somewhere in this ballpark, new cases of TB per 100,000 people per year. So this first group is low incidence TB. The second group, 15 to 50, is starting to be a bit more incidence of TB. Group 3 is starting to be on the high end of TB incidence, and group 4, more than 100 new cases per 100,000 people per year, is high TB incidence and prevalence also. I mean, TB is very present in those places. It's propagating quite a lot, and therefore there's a lot of incident cases. And you can see that it's not enormous, but in recent years, close to 50% of the new arrivals to Canada were from countries that were in groups that were 50 new cases per 100,000 per year or more. And that's quite important because of one thing that has been observed is that, so this is the US, but the situation is the same in the US. This is showing you the rate of number of cases per 100,000 among US-born people. And this is the black line here, which goes down to something like 2.5 per 100,000 per year. Whereas the rate among foreign-born people, as you can see, is 15. So this shows you that in a given population, at the country level here, there is a high level of heterogeneity based on where you are coming from. And in a country like the US or Canada or Australia, like high immigration countries, this has implications in terms of public health. Another type of social structure that we can see, these are the new HIV diagnoses in the US by type of transmission category. And you can see that here, male-to-male sexual contact, men having sex with men, as the epidemiological term is by far where most of the new diagnoses of HIV were carried out in 2019. Heterosexual contact amounted for about 25%. IDU, so injection drug use, was only 7%. But if you think about how many people are in injection drug users, that's quite a high incidence in that group in particular. But you can see that, for example, MSM has a very high incidence here, well, a higher incidence. Now, one other source of heterogeneity is heterogeneity in the pathogen itself. So before that, we saw how population heterogeneity was playing a role in making things change. But here, let's look at the pathogen itself. So this is a graph of, I believe, influenza. Yes, this is influenza. I think, let me see, probably influenza. Okay, I believe it's influenza, but I'm not entirely sure. But anyway, this is showing you the evolution of influenza and for some reason I didn't put it in my notes here, as a function of time, okay? And these are the different strains or clades here, yes, it's influenza, that are present in the population at a given instant in time. And so you can see that starting from a certain clade here, we have a progressive diversification of the viral strains. But what really is important is that if you take a snapshot through 2017, for example, or 2018, what you observe is a variety of viral strains that are propagating in the population. So at a given instant in time, there are quite a few different strains that are propagating in the population. So you can't think of the pathogen as being one unique monolithic pathogen. There's a lot of evolution taking place in the background. And here, for instance, this is in Canada in 2019. Of course, a very weird year because this is mid-2019. This is the 2019-2020 influenza season. But of course, partway through that season, we went into lockdown because of SARS-CoV-2. And that means that the dynamics was quite altered. As you can see here, there's essentially no more transmission taking place after week 15, whereas a regular influenza season would not have this attenuation that you see here. But regardless of this, what you can see is that, for instance, at the beginning of 2020 or the 5th, so the end of January, beginning of February 2020, there were quite a few different types of influenza circulating in the Canadian population. Okay, there were unsubtyped is we don't really know which one it is, but those are specifically subtypes and of type A influenza and type B influenza in blue. And so again, there is heterogeneity of the different influenza strains present at a given instant in time. And the same is true of SARS-CoV-2. So this is a GISAID page, and I'll scroll down. So this data, this course was created for South Africa, well, was given in South Africa. And so what I'm showing here is the latest data from South Africa as of 18 April. And these are the SARS-CoV-2 variants present at a given instant in time. So this is throughout the course of SARS-CoV-2, and you can see how Omicron took over for quite some time, and now we're in another Omicron variant. But so this is, you have them here, 21K, 21L here. Okay, so this to say, even if you look within a single population, so I mean, it depends what you define as your population, but if I'm looking at the population of South Africa in this instance, I am at various instant in time going to observe a certain number of different variants or strains or whatever of the same virus circulating in the population. And so these variants, for example, in the case of SARS-CoV-2, have different properties. Some of them are more resistant to the vaccine, some of us are more sensitive to the vaccine, and this influences what we are seeing. Okay. The second aspect that I want to describe, and so those of you who have followed the course know this, I mean, I've indicated this in the past, but those of you who might be stumbling upon this, this is really what I'm interested in most, and that's mobility and how it relates to the spread of infectious diseases. And that is going to be another source of heterogeneity. So when I speak about mobility, I always spend a little time with this slide, which, so maybe let me not hide as little, oh, I can go here, hide as little as Thucydides as I can. So Thucydides was one of the first historians, and he was alive during that plague of Athens that I mentioned briefly in the first lecture. And here what you have is a text that is part of his history of the Peloponnesian War, and where he describes the arrival of plague, which was probably typhoid fever or something like this, but which is called the plague. And this is the arrival of the plague into Athens. And so you can see that he says, well, it started in Ethiopia, then went to Egypt and Libya, and then Persia, and then it made its way to Piraeus, which was the port part of Athens, and then all the way to the upper city. And this is very interesting in my view because it really gives a very sort of modern description. Well, I mean, it's not very detailed, but it does give you a sense of how the disease meandered its way from Ethiopia into Athens. And so there is this spatial temporal aspect that was present almost 2,500 years ago. So we're not doing anything new, although we have better tools now to study this. Now, why is mobility important? Mobility, and I should move myself here. I'm going to call mobility anything that involves people moving around. Okay, and I'm going to try to convince you over the next few minutes that mobility is really important. It's also complicated. So it's complicated because it involves a myriad of modalities. So you can be mobile on foot if you go to the corner store to get some groceries. You can be on your bike, you can be in your personal vehicle, you can take a bus, a train, a boat, an airplane, okay? So all of that contributes to mobility, which is just how people move around. And mobility is not only multiple modalities, but it's also a variety of durations. If I go to the corner shop, it's different from if I commute. It's different from taking a multi-day trip for work or leisure, or it's different from if I immigrate somewhere or I relocate for some time, or I'm a refugee, or I'm an internally displaced person having to flee a conflict or something like this. So all of those correspond to people making movement, of like moving around, but they're all very, very different. And the overall volume of mobility is almost impossible to evaluate. I mean, it's so incredibly important that I don't know of anybody who would have tried to quantify mobility on a global scale. But it is massive. But understanding mobility is important because mobility drives the spatial temporal spread of diseases. Okay, so I will show you some examples with the Black Death, for instance, but we also know that SARS-CoV-1, for instance, its global spread out of Hong Kong took place for the immense majority of propagation events through the global air transportation network. Well, this is work that I did with some collaborators when we were looking at the H1N1 pandemic, and we looked at how H1N1 was sort of projecting internationally from the source, which at the time was Mexico. And it was easy to see, well, I mean, easy to see, it was possible to see that this propagation was to a very large extent driven by the air transportation network. Now, this is what trade looked like in the, let me go here, what trade looked like in 2012. And what I want you to focus on is this route here. This is a trade route, the Silk Route in particular, that did this and this, and then went into Europe and distributed back through the north. Why is this important? Well, it is important because, well, let's start with this one. This is 100 years later than this trade map that I was showing you, from 1347 to 1352. So 1347 is not showing here, but these are these little patches of purple. This is the arrival of the Black Death into Europe, and you can Europe and North Africa. And you can see that the arrival very much follows these trade routes that we saw earlier. Okay, so here through there is where the plague followed, and then it made landfall in a variety of places in Europe, and then propagated following this traveling wave type solution throughout the continent. And just for illustration, we can see the same type of this is propagation within France. So this is where it made essentially landfall in France. And then you can see that there is propagation that took place over the matter of about 4 years. So this is quite different from what we're observing now. The idea is still the same. The infection followed the trade routes, but we'll see that things have changed quite a lot now. So before I go any further, let me just point out that the Black Death was a very important event worth taking a look at. So this is Yersinia pestis, the bacterium which causes plague. So it was the Black Death was the first of the Middle Age plagues. If you remember, we talked about in the first lecture about epidemiology, I was mentioning the first plague pandemic. This is the second plague pandemic. It affected Afro-Eurasia from 1346 and Europe from 1347 to 1353. It killed an estimated 75 to 200 million people in Eurasia and North Africa. And in Europe, for instance, it killed 30 to 60% of the European population at the time. So this was a major upset compared to which SARS-CoV-2 doesn't even rate. Okay, SARS-CoV-2 has been a fantastic annoyance and has caused a lot of grief and a lot of deaths, but not nowhere close to 50% of the population, which is good. Okay, but so the Black Death was this major event that sort of shaped everything to come in the future of Europe in particular. And I like to point this out because when you've looked at plague a little bit, you recognize that there were some measures that were taken at the time that are still very much in fashion these days, that are still used. So because of plague, a few years after the Black Death itself, so about 30 years after, Dubrovnik introduced lazarettos through which incoming trade merchants, so ships, had to stop for 30 days. And then about 100 years after the plague itself, the first plague, the Black Death, Venice introduced quarantena, which is 40. And so incoming travelers, merchants and ships, as well as their goods, the goods that they were importing, had to go under quarantine for 40 days before being able to disembark and go on to Venice. This is very much something that we saw during the SARS-CoV-2 pandemic. So quarantine is nothing new. There was also isolation of known and suspected cases. So isolation was also used. So if they had people that they knew or suspected had been in contact with cases, they isolated them for 14 days, and then they progressively increased this to 40 days. Plague also led to the improvement of sanitation. So they realized, they didn't really understand what was happening, but they realized that having better water supply, disposing of garbage and sewage in a proper way, inspecting food was improving the situation. And so that the Black Death and the few plagues that followed led to this type of advances. And a bit the same way as we saw with some of the things that people were willing to consume to try to ward off SARS-CoV-2, there were also interesting measures that were taken. So for that last one that I have there is, okay, so one way to fight plague was to find and kill a snake. And because the snake was synonymous with evil, if you put evil on evil, it attracted it and therefore got rid of the disease. So interestingly, several hundred years later, 600 years, 700 years later almost, there are still people that take the sort of the modern equivalent to this type of approach. Okay. Now, what I was showing before in terms of the how plague followed the trade routes is still true. Okay, but what has happened is that the trade routes have also evolved quite a lot. Okay, so whereas before trade was following very specific routes that were quite easy to follow, now the trade routes have evolved. And so let me show you a few examples that sort of illustrate how things have changed. So this is data that's available on the French SNCF, so the train site for France, and it's showing just the duration of a trip from Paris to Bordeaux. So this is 600 kilometers away, and you can see that in the 20s it took essentially 10 hours. This is the minimum duration. Of course, some trips are much longer than this, but a train trip took about 10 hours, and then progressively, with the improvement of train technology, this time has dropped down to, it is now 2 hours trip. And the same way as travel in Europe has become much faster because of this acceleration of train trips. So this is what you see here. This is the high-speed transportation network in Europe. So this is not high speed everywhere, but this is where you can go with proper, in some sense, not everywhere, but with high or relatively high speed transport. And the same way, this is the high speed transportation network in China. And so this here is about 500 million people. This region in China, or the east of China, which is so nicely connected through high-speed train routes, that represents 80 to 90% of the population of China is covered by this network. So more than 1 billion people on that right-hand side are connected by very high-speed transportation. And on a wider scale, this is the global air transportation network. Here I'm just showing the airports and the main routes between these airports, as well as the degree of the airports. That's the number of other airports that a given airport is connected to. And this network is able to disseminate people very quickly. And because people can carry diseases, this network is able to disseminate diseases very fast. This is work that was done in the former Biodiaspora project, which is now a company called Blue Dot in Toronto. And this is work that they did prior to the Vancouver Olympics in, I don't remember remember when those took place. 2012, 2014, I can't remember. But anyway, the idea was to see how far away from Vancouver were the different parts in the world. And that's, so look at just the base of the map, the color, and that shows you how long it takes to go from anywhere in the world to Vancouver, and at the minimum travel time, of course. And you can see that there are very few places where the travel time is more than 24 hours. There's a few isolated places where it would take you more than 24 hours, but altogether, you can make that trip in very little time. So that means that in terms of Vancouver being potentially the recipient of diseases, which is what is shown with these bars here, well, that's very quick. And the number of people that I should point out, I mean, the number of people that who use airline transportation has increased even since the 2000s. If you look early 2000s, it was about a billion and a half passenger trips, and it's increased to 4.5 billion in 2019. I should point out this is data from the World Bank. I don't think they have updated it yet. Of course, there is a collapse of the number that you can see in 2020 and 2021, but it's not shown on this graph. Okay, but this is, so the number of passengers transported by airplane, and you can see that this has increased a lot. So in terms of, you can go quickly very far. Now, I'm interested in heterogeneity, so I want to explain why, because you could think also that, okay, so we could consider the whole world as one, but there is also a lot of heterogeneity happening on the spatial aspect. And so if you think from a jurisdictional point of view, the divisions, the political divisions, nation groups, nations, provinces, states, countries, cities, etc., they all work as little entities. So first of all, there can be difficulties traveling between jurisdictions. So here I'm illustrating, I believe it's the border between the US and Mexico. I don't remember where, but this is sort of illustrating how difficult it can be to go from one place to the place very close to it. So travel between jurisdictions can be complicated. But also, if you're thinking about the public health aspect, data and policy are integrated at the jurisdictional level. So this is very important. So as someone trying to make contributions in public health, you will be confronted to the fact that the data that you collect is collected typically at some jurisdictional level. It can be, putting myself up, it can be, like for example, in Canada, we have provinces, and provinces are the units that collect data. And so the data you have is going to come with a certain geography associated to it. And the same way, the policies that are going to be implemented are implemented at some jurisdictional level, typically the country, but for example, here in Canada, things are decided at the provincial level. So that's one thing. And it's important to see that travel typically is, if you're looking at long-range mobility, it is going through a variety of jurisdictions. So everything is quite fragmented in the way it presents when you try to understand it. But mobility altogether is super important in the context of health, because these are the main 2 points that I want to make. So first of all, whenever you travel, whenever you are mobile anyway, you bring with you your health history. So, for instance, latent or active infections that you may have. So, for instance, people that, yes, I should, people that have active or have latent TB, for instance, they will move to another country and TB remains latent for many years, but sometime in the future, maybe they will become, the TB will reactivate and they will become infectious to others. H1N1, polio, HIV, etc. All these infections that you have, but also immunizations. So what type of immunization, if any, is present in the country that you're coming from? And what is it in the country that you are? So if for instance, you go somewhere and there's no vaccination against measles, or it's very bad in terms of how often it is done, and you're yourself coming from a region that's vaccinated, but you're not vaccinated, well, you're at risk of contracting measles and you can bring it back. I like to give this example, health and nutrition practices. Being French from France, I am forbidden from giving blood in Canada because it is possible that I was infected with a prion, like the mad cow disease. And so this part of my health history is traveling with me. And what's really important as well is to remember that pathogens don't care about borders and they don't care about politics. As was amply shown by SARS-CoV-2. I mean, SARS-CoV-2, a lot of countries closed their borders in some way. They tried to hinder movement and so on, but SARS still essentially made it. And I'll talk about this a little later. So the first SARS, for instance, the one that happened in 2002, 2003, essentially started propagating starting on the 21st of February, 2003. There was a person who came to Hong Kong for a wedding, and he went into a hotel, and in that hotel he infected several people. And these people, Hong Kong being a very active trade place, these people flew home to a variety of locations, and with them carried SARS. That infection was resolved much faster than SARS-CoV-2. The last country with local transmission was Taiwan, and Taiwan was removed from the list of places with active transmission on the 5th of July. So it's several months, but in several months, the disease went to 28 countries or territories. So it was quite an impactful disease in the sense that the case fatality ratio was quite high. So it killed much more per infection than SARS-CoV-1 has, fortunately. And in terms of the spread, this is, so I've shown in black China because the virus was propagating in mainland China until it made it to the global air transportation system a little later, like the 21st of February, what I was mentioning before. So that's where the virus originated, and then it moved to Hong Kong. And from the moment it hit Hong Kong, this is the number of days that it took for the different countries that were affected to import the virus. So you can see that, for instance, Canada and the US and Australia, Southeast Asia here, were infected quite quickly. And then a few places were infected not as fast. So New Zealand and India took more time, but altogether propagation took about 80 days. Okay. Another instance of spatial temporal propagation that I think is really interesting to motivate the type of problem we're looking at is this. So this is the situation that prevailed in these countries that I'm showing here, so Central to West Africa, essentially. And that's in terms of the percentage of kids who had received 3 doses of the oral polio vaccine at the end of 2002 or 2003, I can't remember, thereabouts. And you can see that there are countries that are doing quite well. I mean, this is 80 to 90% of vaccination. There are countries that are not doing so well, and Nigeria stands out here as being very low vaccination coverage. So what happened at that time is that in the north of Nigeria, there was a vaccine scare. You never know really where those scares come from. There were some rumors that circulated about properties that the vaccine would have. And because of that, things became hard enough that the authorities in north of Nigeria, it's a province called Kano, they decided to interrupt vaccination at this point. Sorry, I had to take a little break to sort out a problem with the size of the video file on my computer. Okay, so at the end of, at some point in 2003, not the end, at the end of 2002, there was this vaccine hesitancy that started to pop up. And sometime in 2003, the authorities in the north of Nigeria took this measure to suspend vaccination. They didn't do so for very long, it only lasted a few months, but the impact was easy to see. So these are the countries in the area and the number of cases of polio the different years. And what you can see is that things were really good until 2002, and then there was this outbreak that started at the end of sometime in 2003 and lasted for some point. So what I'm not showing you here is the numbers for Nigeria. So Nigeria had much, much higher cases, caseloads, and so I should show you the labels. But so what you can see, and this is quite important, so a sort of low vaccine coverage in one region, despite having high vaccine coverage in other regions, had consequences in all the in other countries. I mean, had consequences in all neighboring countries, and this is quite an effect of the fact that people are moving between locations. And in the end, if you look at what happened following this this episode, you can see cases in Nigeria that spread on to neighboring countries. There were also at the time cases in India. India hasn't had a local case of polio for quite some time now, but at the time they were still having cases, and some cases went in various places. But that effect of vaccine discrepancies between places is very important, and it's one of the reasons why I think it's really important to try to think of things in space. And I will come back to that later in the course. And the last thing I want to talk about in this lecture is waves of COVID, and I will go quickly, but these are some notions that I think are important because they combine space and heterogeneity at the local level. So in terms of what happened, it's not really clear, but what we know is that what I will call amplification took place in Wuhan. So amplification is the phase of an epidemic during which the number of cases sort of starts to blow up locally. I will come back to that in a later lecture. It's not really clear when things started, where they started precisely, but we know that amplification took place in Wuhan. And so in terms of what happened, the timeline of what happened, there were a cluster of pneumonia cases related to a seafood market. At the end of December, there were reports that were made to the local government. At the very, very end of December, publication was made. I mean, in the sort of international health surveillance community, there was a publication with WHO. And from then on, a few days later, SARS-CoV-2 was identified as the causative agent of the disease that was being investigated there, which is very quickly. I mean, I want to stress this in a SARS-CoV-2 world, everything happened very quickly. We will later on, when you think about vaccines, the time that it took to develop vaccines was also very impressive. But anyway, so in early January, SARS-CoV-2 was identified as the agent. Around the 23rd of January, there was a lockdown in Wuhan and Hubei province, where Wuhan is located, a face mask mandate. But by the end of January, the virus had already been found in all provinces of mainland China. So that lockdown came a bit late. And this is something I'll come back talk about more in later courses. Outside of China, the spread started very early as well, and so the first few cases that were detected were in Thailand and Japan, where they had arrived essentially at the beginning of January, and they were detected a bit later, but the arrival in those places were 6th and 8th of January. And then the propagation started happening. And it's actually quite clear that propagation must have started earlier. The first report to the authorities in Wuhan was on 27th December. First detections for cases on the 6th of January. This is a very short timeline, so amplification must have been going on for quite some time earlier than this. And actually there is a sample in France, for example, that was collected from someone on 27th of December that, as far as I remember, has been positively tied to SARS-CoV-2. And there were also studies in the UK and Italy that showed undetected cases in the pre-pandemic period. In terms of the spatial spread of the disease, so to illustrate the speed of spread, what I'm showing you here is the number of countries or territories, so top-level administrative jurisdictions that are reporting cases of SARS, so SARS-CoV-1, and SARS-CoV-2, so COVID-19, as a function of the number of days since the start of spread. And what you can see is that originally things look quite the same. The number of countries and territories reporting cases sort of follows the same trajectory about until a month into the pandemic, at which point SARS itself spread to a few more countries and stopped spreading after about 80 days, whereas SARS-CoV-2 spread to many, many other countries. There's 196, 93, I can't remember exactly, countries in the UN. And you can see that we're nearing this number after 100 days. So most places had imported SARS. But as I was saying, what's important as well for SARS is this heterogeneity of the variant that's spreading. So this is showing you as a function of time the variants of concern. So these are not the only variants that were spreading, but they became dominant at some point in the spread. And this is the number of jurisdictions, again, top-level jurisdictions, reporting cases of the different variants. So one remark, you can see that this is Omicron, that came in late 2021 and is still ongoing. You can see why Omicron had everybody so worried, because the others had a sort of establishment phase during which propagation was to not a lot of countries, and then a kickoff phase, whereas Omicron went very quickly from not being detected in any places to being detected in many, many places. And you can see that in terms of the timing from the date of first detection. So this is Omicron with its very, very fast propagation to many jurisdictions, whereas the other variants took much more time to become established from the time of first detection. There's a little issue here. I should fix this. This variant is badly attributed as being it's Delta. I think Delta, the first sample in the database, goes back to 2019, which I think is just a fluke that I need to remove. But anyway, so you can see how there's a spatial aspect there, but there's also a heterogeneity, because at some point a lot of places had most of those variants still spreading, and these, as I pointed out, these are just the variants of concern, but there were also many other variants spreading. Okay, so that's it.